Start? Okay, so we will restart. Good, so first of all, the first thing you'll ask yourself is, what is actually G2? Well, G2 is Lie algebra or Lie group with the following Lincoln diagram. And another important thing that we've already seen, it is a subgroup of SO7, and it is sort of characterized by stating it's the subgroup that leaves invariant the following combination of forms. So this will be completely unilluminating, and I'll give you a much better definition in a second. Oops. Where dxijk is obviously dxi, which dxj, dxk. So SO7 will act on this object, and the subgroup that actually keeps it invariant is G2. Another way of saying this is the automorphism group of the octonions, but perhaps for us the most relevant thing is that it is the group that for the 8 spinor representation of SO7, if you fix one vector in it, then G2 is the subgroup that leaves that invariant. I.e., what we're doing is we're looking at SO7, 8, and that breaks to G2 as 1 plus 7. And that's, of course, also how I brought up the group in the first place, that this is one way of seeing that for 7 manifolds, you can have spinors that are coherently constant, or you have a chance of getting that if you actually have a reduced holonomy G2. So as a holonomy group, exceptional holonomy group, it's relevant for, of course, 7 manifolds. And basically what it is characterized by is, again, a 3 form. So it exists phi 3 in the third cohomology of this manifold. That's called this manifold X, such that d phi and d star phi is 0. And essentially here, this phi 3 usually you can write in the form that phi 3 takes the same in star with the dxijk replaced by ei wedge ej wedge ek, where the ei's are 7 binary. And the metric is given, it's completely specified in terms of this 3 form. So the metric is gij, and it's given in terms of determinant, bij to the minus 1/9, bij, and where bij is the following combination of 3 copies of this 3 form, which is also called the G2 form, phi I, K1, K2, wedge, phi J, K1, K3, K4, wedge, phi K5, K6, K7 times epsilon K1, K7. Okay. So a lot of these, these forms, in fact, I didn't sort of go into this before because I wanted to get to this thing. Essentially, these forms in spaces with holonomies, they're quite omnipresent, and also you know them from Calabi-Yau's. Basically, let me just sort of give you a very brief sort of recap. So, for special holonomy, or reduced holonomy, let's say, there are sort of invariant forms which can be constructed out of this covariantly constant spinor. So we have some nabla epsilon is equal to 0, and then I can construct out of sort of an antisymmetric product of gamma matrices 1 to p, and sandwich this between two spinors, forms p forms psi p. And if we decompose these with respect to the holonomy group, let's call that G, and then the invariant forms and the singlets, so in the 1 are the invariant forms. And for G2, this is precisely phi 3 and star phi 3. For the Calabi-Yau cases, this is sort of omega 1, 1 forms, and the holomorphic n, 0 form for Calabi-Yau n-folds. For spin 7, if we do that kind of thing, then actually this is a 4 form that's self-dual. And one key property of all these things is that they actually define what's called calibrated subspaces. And that'll be important for later on for looking at brains. Okay, but let's stick for now to G2. So how do I actually find that there are these 3 forms and a 4 form which is just Hodge dual to this 3 form? So the cohomology for G2 decomposes into, well, there's H0, H1, H2, H3 plus Hodge dual. Let's say of X. And this is as moved to R. H1 is 0, at least for special for pi 1 is 0 for Ricci flat spaces. H2 has a decomposition into H2 in the 7 representation of G2 and the 14 representation of G2. And finally, the 3 cohomology has a decomposition into a singlet plus a 7 representation plus H27. 3. Okay, so these guys here at the bottom, these are all G2 representations. Right, so this is essentially this possible decomposed with respect to G2 in this case. Right, so these are representations of G2. If we want holonomy exactly G2, so if the holonomy is exactly G2 and not less, then in fact these guys here have to be 0. And then we're left with essentially these invariant forms in H3, 2 forms and 3 forms. So in fact the G2s, this one here is just the phi 3 invariant form. And in the Hodge dual H4, there will be star phi 3. That's the 4 form. And for G2 manifolds, this 4 form is exactly Hodge-Dot to this one. We're not looking at the more general things. And then there are the 2 forms and 3 forms. So in fact, G2 compactifications will be characterized by these 2 numbers, B2 and B3, and for some given phi. Okay, so... That's right. So in fact, you will get not exactly G2 if you actually have these guys. So if you have exactly G2, you can show that these guys just have to be 0. So in the case when you now consider looking at compactifications of this in M theory, so the characteristics for this are B2 of X and B3 of X, which are this H2 and H3, as well as then we have some phi 3, which is this invariant form. So in M theory, we have the metric and C3 form. These are the bosonic fields of the 11-dimensional supergravity. And now one thing we can ask is when we do a KK reduction, what actually is now the spectrum of this 4-dimensional theory? So of course what we usually do is we take this 3 form and we expand it in the forms that we have at our disposal here. So we have CMNK is now, for example, we can expand in terms of the 3 forms. So the alpha equals to 1 until B3 of X in terms of 3 forms alpha. And then the expansion coefficients are scalar fields, real scalar fields in 4 dimensions. Yeah? So X is a coordinate on R1, 3. So we get B3 of X many real scalar fields. This is partnered, so of course this by itself can't be sort of the component of a chiral multiplet in 4 dimensions, so we actually need to supplement it also by looking at the metric. So the GMN fluctuations are essentially given in terms of some, say, HMN times some functions phi of space times X, the metric. And they will actually make this a complex scalar field. So this here will actually satisfy Ehrlich-Nerowitz equation, and then we can map these symmetric tensors HMN with the 3 form that we have in the G2 manifold. So let me actually write this down. So actually these HMN can be mapped to phi M and K, H, M, L, which are 3 forms, N, K, L, and 1-to-1. So in fact, these are also giving then B3 many real scalars, which then together with what we had from the C3, so these guys here and these guys here combine into B3 of X chiral multiplets, including the fermions that we have not discussed here. Okay. Now we also have 2 forms, and if we expand the 2 forms, the C3 in the 2 forms, this is very similar to what we did earlier in terms of the 62,0 theory. So the B2 of X, we have C3 expanded now in terms of, say, some omega I2. And of course, what we get here is gauge fields. So these are abelian. So you get B2 of x after adding in the gauge genus for this, B2 of x many vector multiplets. And one other thing to note is that this is so far a completely boring theory because these chiral multiplets are not charged. These are U1 vector multiplets. Okay, so this is really maximally boring. So what I've assumed in all this is that this G2 manifold here is smooth. No? And this is essentially giving you something completely uninteresting. So how can we improve the situation? Well, we learned non-abelian gauge degrees of freedom usually come from C2 mod gamma type singularities. So one way to approach this problem is, can we build G2 manifolds that have, that are based on some kind of C2 mod gamma orbifold that is embedded into this geometry? And indeed, that's possible. But for this, we first need to sort of understand a little bit how to study M theory on C2 mod gamma ADE. So to improve this, singular. And the clue, as I said, is consider C2 mod gamma ADE somehow embedded into a G2. So before going there, let's actually first think about what is the dimension reduction of M theory on such a non-compact K3 manifold. Okay, so step one will be, let's consider M theory on C2 mod gamma AD. And the second step will be fiber C2 mod gamma ADE over, so 4 plus 3 is 7, over 3 manifold. Okay? And then argue that this actually has a G2 structure, or this is a G2 manifold. And indeed, we will see that this is possible. Cool. So how do we get to point one? Well, this is the usual story. We already looked at this orbifold, and we learned that when we go to and blow it up and resolve it, we actually get sort of this collection of P1s, right? So in fact, M theory on this non-compact Calabi-House threefold, where the geometry is y squared is x squared plus z to the n plus 1. So for an, gives us, in fact, a 7-dimensional super Yang-Mills theory with an gauge group. So where do the fields come from? Well, first of all, we have C3, and we can expand C3 along these one cycles, these P1s, these two cycles. So we can actually expand C3 along omega I2, wedge AI, where now I equals to 1 until n. And these are the volume forms. The C2 mod gamma ADE resolved P1s. So this is sort of in the case where we've blown up the singularity and we've see these P1s, self-intersection -2 up here, so the n of these. And this gives us n U1 gauge fields. So we didn't really improve the situation yet, But we also have now M2 brane wrapping modes. That can sort of wrap a collection of these P1s. Let's call these sort of some vector VI, P1I. So, and these are charged under these U1s. In fact, these furnish exactly the W bosons. Which become massless. And the volume of the P1 goes to 0, right? So the mass of these is basically set by the volume of these P1s that they wrap, or by this collection of this VI, PR1I. And so as the volume of these shrink to 0, these become massless modes, and in fact, in this way, we get an SUN+1 non-abelian gauge symmetry. So, if you've never seen this before, there's a classic paper by Witten, I guess from 97 or something, where he details this in a lot of detail. Okay, another way of seeing this is to actually, right, we were talking about this M theory on this orbifold singularity, which is a local K3, a non-compact K3. An alternative way to see this is to use dualities. So you can, for example, unpack some of the very 90s tools of dualities. So other evidence for this. That C2 mod gamma ADE gives rise to 70 Young Mills as G equals to ADE, is considered that M theory on a K3 is supposed to be equivalent to heterotic string theory, say with E8 times E8 gauge group on T3. So that's one of the classic string dualities, and one way of seeing or arguing for this is that, well, the moduli spaces for these theories agree. So you have on the one hand the heterotic string on T3. The moduli space is the Narayan moduli space of this compactification on the torus, right? So this is essentially a well-known SO3, 19 mod SO3 times SO19 modulo the T duality group, which is SO3, 19 Z. And then there's also the string coupling. So in heterotic, this is the string coupling. And this is the Narayan moduli space. For the T3 reduction. This is the heterotic picture. And then for the M theory on K3, this moduli space is in fact the moduli space for Einstein metrics, which are then automatically Ritchie flat on K3. And here the R plus factor is the volume, the overall volume of the K3. Okay? And so just from this point of view of the parameter space of these two compactifications, you could argue this is a slightly more refined version where we can look at, how exactly, for example, the H2 of the K3 is mapped, how the periods of the hyperkähler forms is mapped. Perhaps I will skip this in the light of time, but so the heterotic string on T3, we can, of course, depending on what type of Wilson lines we turn on, break the gauge group to E8 times E8 or any subgroup thereof, and so there should be a counterpart of that at some point in the modular space of the K3 where we have essentially also this non-abelian gauge symmetry. Okay, so this is essentially a way of saying this duality is sort of adding some more evidence as to what this theory M3 and K3 is, but it's also an important duality because it actually will give us a way of understanding some of these G2 geometries. Because as I told you, the K3 compactification or the C2 mod gamma compactification we'd like to use to then construct G2 manifolds by fibering this over 3 manifold, and then in this, if we take this duality and fiberwise obliged to a fibration of a 3 manifold, then this is heterotic on a Calabi-Yau threefold, which is written in terms of an SYZ fibration T3 over M3. Okay, so right, so the way to now actually get from K3s to G2 is to actually fiber this. Just our C2 mod gamma ADE over M3. Again, there's some evidence such that the resulting space is a G2 holonomy manifold. Again, there's evidence from this M-theory heterotic duality. So we can, so Calabi-Yau threefolds have what's called SYZ, Strominger-Yau-Zaslow fibrations. T3 fibrations. So we can write them as some T3 fibered over M3, where M3 is some 3 manifold. And these are so-called special Lagrangian fibrations, so they're with calibrated cycles. Anyway, so these preserve, so heterotic on Calabi-Yau 3 of this type preserves 4-dimensional n equals to 1. So applying fiberwise duality, we expect that there is then a K3 over M3 that also preserves for the n equals to 1. And so it's G2. And it's just sort of to add evidence for this, but I'll actually give you some derivation of what the theory is that we get by reducing. Okay, so at this point, we'll get to sort of studying the first sector of this class of theories, which is the gauge theoretic sector. Because we're now looking at a non-compact K3 C2 mod gamma ADE, and now we're reducing this further, or refibering this over a 3 manifold. The whole thing is non-compact. With the coupling gravity, we're just looking at the gauge sector of G2 compactifications. So we start, right? So C2 mod gamma ADE resulted in 70 Young moles, and basically, yes, sure.
Is it clear that whenever you have a compact G2 with the non-abelian gauge group, that this is always locally of that type?
Well, you can essentially then always. So it's about as much a theorem as it is for the Calabi-Yau fourfold case, because you can take a local limit, and you need to get these gauge degrees of freedom. I think it's probably less strong than with the Calabi-Yau fourfolds, because we don't know very powerful theorems about G2s yet. But certainly, whenever you have a 3 cycle where there are gauge degrees of freedom localized, you will have to have, and the ADE gauge groups, you will have to have a singularity above it. Locally, what this means is you will have to, the geometry is then, I think, characterized in terms of an ALE vibration over that. And that's exactly what we'll get to. So, yeah. So the 70 super-Young Mills theory, well, if we reduce this, we'll now find a certain theory on M3, and studying that will tell us what actually describes this 4-dimensional n equals 1 sector. That's the gauge theory sector of this compactification. Okay, so let's start with our, just looking at, again, first of all, the supersymmetries. So we have an SO6,1 Lorentz times the 70 super-Young Mills theory has an SU2R symmetry. And we'd like to reduce this to something that's a compact 3-manifold times the SO1, actually let me turn this around. So this is our Lorentz group in 4 dimensions. And the local rotations on M3 times the SU2R symmetry. And we'd like to retain now supersymmetry, namely n equals 1 and 40. The supersymmetry parameters for the super-Young Mills theory in 7 dimensions is this 8, 2. So there are 2 under the R symmetry, and then the spinor representation 8. And when we reduce this, we'll just get essentially 2, 1, 2, 2 plus 1, 2 chiral and anti-chiral spinners in 4 dimensions, and they transform in the 2, 2 of the SO3R and the SU2R and the SO3M. So this is not preserving any supersymmetry. We have to actually do what is you always have to do in this sort of situation to preserve supersymmetry. You actually have to twist, identify these two groups, or better, you redefine what you mean with the local rotation group along M3. So twisting means we identify a diagonal of the SO3 and say, right, these are the algebra states of the SO3R, and then the decomposition gives us 1 plus 3 plus 1, 2, 1 plus 3. And indeed, once we've done this, the n equals to 1 supersymmetry is sort of coming from the singlets and the spinners in 4 dimensions, which are now exactly 4 supersymmetries. So n equals to 1 in 4D. So this is just sort of a back-of-the-envelope calculation. Actually, what we have to do is really do the dimension reduction of the 70 super-Young Mills theory with the twist and show that this is indeed consistent and preserve this. So the fields of the 70 super-Young Mills theory now also will have to be reduced. And you see, without doing the twist, you'd be looking just at a product of C2 mod gamma times a 3-manifold. By doing the twist, essentially this corresponds to now fibering the space over M3. So fibering this 8E singularity over M3. And that the claim is that this actually is going to give us a G2 manifold. So likewise, so the gauge field, the scalars and the fermions, right, they transformed in the 7.1 and they now become the gauge field in 4 dimensions plus a 1 form along the 3-manifold. The scalars, well, these stay scalars, but then are also 1 forms in this twisted Lorentz group. And the fermions, so we've seen these already, but I'll just have to write it down because actually this decomposition will become important. Okay, so all of these here are the representations under the SO3 twisted group. So this is now redefining what we mean by the local Lorentz group along M3 by an R symmetry transformation. So what we see here is that after we've twisted, the gauge field components, let's call this your sort of, so it's make this your boldface. This is A mu, this is the four-dimensional gauge field, and this is W. Then W corresponds to one forms, and likewise phi on M3. The fermions decompose into chi alpha, psi alpha, chi bar alpha dot, psi bar alpha dot. And again, of course, there'll be superpartners to these phi and W's, which are also in the 3. So this is psi alpha and psi bar alpha dot. They're also one forms. And then there's sort of the gauge sector, which is A mu, and the chi alpha, which are just 0 forms on M3. Okay, so what we have to determine now is actually what type of gauge configuration or field configuration along M3 will give us actually a supersymmetric four-dimensional n=1 theory. For this, so to determine the field configurations along M3, which yield for the n=1, we have to look at the BPS equations along M3. So we said the delta psi, delta chi equals to 0. And what we obtain here is a set of F-term and D-term equations, which is, I think, quite standard. But the form of these is something that is slightly different from what you might have seen before. So the first one is this equation Fw minus commutator phi phi. So Fw is just the field strength of W. Then dW phi is 0, and then the D term condition d dagger W phi is 0. So these equations are going to be governing the type of field configurations that are going to give supersymmetric, n=1 supersymmetric gauge theories after reducing the 70 superangles on this curved manifold M3. So they're very similar to things that you will get if you take n=4 superyoung mills and you reduce it on a curve, or Hermitian-Young mills and reduce it on a curve. And these are like the Hitchin equations in that case, where the fields on the Riemann surface on this complex curve satisfy essentially equations of this type. But now this is sort of on the 3 manifold. So let me just write down this in a few in the comment. So this is similar to, say, looking at Hermitian-Young mills on sigma, a complex curve, where then you get the Hitchin equations. Something where now f z bar minus phi bar is equal to 0. Yes. So in this case here, phi is, so in this curve case, phi was sort of holomorphic one form, and here we get phi and also W are one forms on M3. So this was here on sigma, and this is now we're getting the system of one forms and equations for them on M3. Okay, so what the goal is now, solve these equations and that should then define an ADE singularity fibered over M3. And in fact, what we get for phi is sort of matter and couplings. Cool. Of course, solving these equations, if you look at them, is quite complicated. Yeah? So this is usually not some easy feat to do, even in this case of the Hitchin system, where you have a complex curve. Here we have a three-manifold. This is quite a complicated system of equations. And so we'll make some simplifying assumptions, right? So we'll start with some simplifying assumptions. Namely, we'll say, let's assume that these phi's commute. So then this implies that Fw is equal to 0. And let me just write down again the equations here. The W phi is 0. These were the three equations we have to solve. Now, on a three-manifold, there's a choice whether we have pi1 trivial or not. If we have pi1 equals to 0, then in fact W has to be 0. Then d phi is d dagger phi is 0, so phi is 0, so that's not very interesting. So the question is, well, basically argued for you is that if pi1 is 0 of M3, then we won't get any interesting solutions. You could now look at configurations where pi1 is non-trivial, but there's sort of a simpler set, and one motivation for that is in the back of my mind I have that. So for many, for many G2 manifolds, these kind of three cycles are actually S3. So I would like to have some way of studying these systems on S3. One way of sort of remedying this is, well, here I actually made an assumption that phi is actually regular. So this is always on the assumption that phi is regular. So we could allow for phi to have singularities. And this is actually natural, so if you actually have studied F-theory local models, phi has poles there as well, so this is something very natural to consider. So we'll relax this condition that phi is regular and actually allow for singularities, and then ask what kind of equations are we solving then. Okay, so we won't quite get to the sort of finding the full spectrum today, but I will sort of give you a description of what kind of cohomological tools we'll need to actually find now the field configurations and the spectrum for this kind of set of equations when we allow phi to be actually singular. Okay, so for simplicity, let's recap. So phi is a one form, and it's some adjoint valued. In the gauge group, say G, and I'll put a tilde here of the 70 Supergravity-Mills theory. This is the gauge group. The simplest way to now have a non-trivial gauge configuration is to allow phi to actually take a non-trivial bev in a U1 inside this G tilde. And what this means is phi Higgs is G tilde to G times U1. Okay, so we have some adjoint of G tilde, which will break to an adjoint of G plus R of some charge U1 plus the conjugate, say, Q. So the simplest setup you can think of is, for example, SUN plus 1 going to SUN times U1 with fundamental matter. Okay. So if I consider something like this, and I also allow this phi to actually have singularities, phi is to have say on some subset gamma inside M3, I can ask, so how do I actually now solve these equations? What are the type of equations that I have to solve now? So the Hitchin equations, or these generalized Hitchin equations that we have here, phi commutes, we have pi 1 is still 0, so W is 0, so we're actually looking at d phi and d dagger phi is equal to 0. So in fact, the singularities I can now model in terms of actually writing phi as df, and then the singularities are essentially saying I have delta f is equal to not 0, but actually rho, where now rho I should really think of as some charge configuration on M3, and then f, which is just df is phi, is just the electrostatic potential. Okay? So this brings basically the solution of this Hitchin system to a problem that we all studied as undergraduates at some point. Maybe not on some general 3-manifold with some complicated charge configuration, but that's certainly morally speaking what's going on. So we have, say, the 3-sphere, and now we're putting into this some charge configuration. Okay. Strange program. They can be loops, they can also be just point charges. And along these, so this is gamma, and along gamma, this are the singularities. Another maybe useful way of rewriting this, an alternative description, is to take this charge configuration, excise this out of the 3-manifold, and actually consider sort of some neighborhood of this gamma. So T is some tubular neighborhood. And so we've got these tubes that are sort of around this. And now I'm actually taking out from M3 this neighborhood. And then the resulting space, so M3 goes to this space here. This has a non-trivial boundary. So let me call this here again M3. So it's a bit... This is the object we'll work with, so let me just denote this by M3, but this object has a non-trivial boundary. And we can now have phi irregular, but with boundary conditions along this complement of T gamma in this boundary. Okay, so this is actually the setup we'll study. Phi is regular. We've taken out the tubular neighborhood from this charge configuration, and we now have to impose suitable boundary conditions along the boundary of this new space, M3. So M3 is basically everything. We've taken out this light blue tubes. Okay, and this is now a problem that we can rewrite, and we can write down the cohomologies that count the zero modes of fields quite nicely. Okay, so the setup that we are now looking at is we have, so putting it all together, so in summary, we have some M3 where the boundary is non-empty. phi is regular, is 0 with suitable boundary conditions. And the boundary conditions will be part of the discussion that I'll go through in some detail. So when phi is equal to 0, we just have G tilde as a gauge group. But when phi is unequal to 0, the gauge group is broken to G times U1. And if you consider this sort of, when is the group actually enhanced to G tilde, so when phi equals to 0 actually is a condition now on all three components of this field. And so it is actually generically codimension 3 in M3. So we expect these local gauge enhancements to occur at points. In M3, and so these are in the total space, this K3 over M3, they're codimension 7. Yes, and so I told you before this G tilde enhancement when phi equals to 0 corresponds to the loci where we have some matter representations, like here. So matter, the most generic setting, will actually be occurring in codimension 7 in G2. So this is probably something, if you've heard about G2 manifolds, codimension 7 singularities are the essence of building geometric engineering in G2 manifolds. This is basically where this is coming from. Right, so the gauge degrees of freedom are localized on M3, so that's codimension 4, in the G2 and codimension 7, we have the matter. Okay, so, right, what I will do tomorrow morning is actually go through a derivation of the zero-mode spectrum, and that'll basically map, given some Higgs field or some configuration phi on a 3 manifold with a boundary, what is actually the cohomology that counts these zero modes, and then give you some examples of what type of models, or what kind of charge configurations give rise to interesting spectra. And then the main part of tomorrow, what I'll do is actually discuss how all this fits into now a compact G2 manifold, how these geometries actually are now reconstructed from this gauge theoretic picture, and then also what kind of compact geometries are actually there. And then the last lecture I'll talk about what kind of branes are present, and then what properties they have. Right, it's time now, right? Okay, cool. Thank you. Are there questions? Are there any questions? Yes?
For many G2s, M3 was S3.
Yes.
What did you mean? So, what did you mean by that?
So what I mean is, when you look at compact G2 manifolds, and there are very few, and I'll tell you roughly what type of G2 constructions there are, where we have some control over the statement of what calibrated 3 cycles are. They turn out to very often be just S3. So, for example, in this huge class that I mentioned at the beginning that now was recently obtained, a lot of these are, in fact, for a subclass of these, there's a huge number of S3 calibrated associative cycles. And they're just all homology 3 spheres. That's why the 3 spheres seem a good starting point. But you could put something else there and construct another manifold. Yeah, so sure.
Then
Yes?
phi doesn't have to be 0, and so pi 1 was 0, was used to.
Yeah, I mean, this was sort of a simplification. You see already in this setup, you will get quite a rich kind of class of Higgs bundle configurations. you could now allow, you could have an onto pi 1, and then you could look at what type of Ws you can turn on, and then study this combined system. It's already, with this, you get a lot of mileage. That's why I'm focusing on this. Just,
Thanks.
yes? Okay. Any other questions? Okay.
Okay. Before we thank Sakura again, we can just a reminder, we meet at 5 o'clock after coffee for a discussion session with the speakers of the day. Thank you very much.